Welcome to Baylis Physics Lab. Today, Newton's first law of motion, or the law of inertia. An object in motion, or at rest, will stay in motion, or at rest, unless acted upon by an outside force. Objects prefer not to change. Not at all. They don't want to change the way that they are moving. And sometimes, people too. Now, I don't know about you guys, but there was many times when I was peacefully enjoying a nice long weekend after a hard week of school. And the next thing I hear was, "Get up! It's time to go mow the lawn." And I was like, my body sitting under these covers right now is not moving a single inch. Not one little foot, my arm, not my head. I'm going to sit here and enjoy this for as long as I can. There ain't no way I'm going to hop out of here and go mow the lawn. But the next thing you know, my dad comes in and nicely helps me get out of the bed and pop out here and get going. And then something amazing happens. Once you start moving, once you start going, you get a little bit of water, you brush your teeth, and you get dressed and you get going. It's all right. It's not as bad as it used to be when you were sitting here under the covers, just hoping that your dad forgets you unless your siblings do it for you this time. And then once you get going, it's not as bad as anymore. Now, I want you to channel that feeling, and it'll help you understand what we're about to talk about today. So imagine a book on your desk, just sitting there. Just sitting there. It ain't going anywhere. And it would have a velocity or a speed of 0 meters per second. And guess what? It's going to stay right there at that 0 meters per second forever. Unless you decide to pick it up and read it. And you would be the outside force in that situation. Now, let's take another example. Imagine a hockey puck racing across the ice rink after this player striked it. The puck seems to go on forever. However, does that actually happen? Well, let's take a closer look. Let's say that the hockey player strikes the puck and it starts racing across the ice. Let's just say that he struck it and it started to move at 20 meters per second. All right, so how to read velocity is in 1 second, how many meters will the puck travel? And so this player hit it with a velocity of 20 meters per second. That means that every second it's traveling another 20 meters. And because of Newton's first law, we know that the velocity will continue to be at 20 meters per second. Okay. Does this really happen? Yes. But, like we looked at before, at the very beginning, unless it is acted upon by an outside force. And we will talk more about that in our next video when it comes to Newton's second law, but I'll give you a brief intro to forces, because friction is the common force we talk about when we're changing force or changing direction. The force of friction is going to always be parallel to the direction of motion. So if we're going this way, and so this is our puck in our ice rink, just like we had over here in this previous example, it's just being blown up right here. But the force of friction must be parallel to the motion. And so the force of friction isn't coming up here, it's not down here, It's not over here. If our motion's this way, the force of friction must be parallel and in the exact opposite direction. And this is why, if we hypothetically had an ice rink that went on forever, the puck would eventually stop. And that is because there's an outside force of friction that will cause it to stop at some point. Now, do all objects move the same way? I don't know. You tell me. Is it easier to push your dad's Tundra or a shopping cart at the grocery store? Well, we'll find out exactly why that is in our next video when we talk about Newton's second law. See you guys there.